The world's largest nuclear fusion experiment is happening right now in the south of France, and it's unlike anything we've seen before. This massive project, involving 35 countries, aims to create the most powerful nuclear fusion reactor ever built. Imagine a machine that mimics the energy of the sun, right here on Earth. The reactor, called a Tokamak, will heat hydrogen atoms to 150 million degrees Celsius, 10 times hotter than the sun's core. Powerful magnets, some weighing as much as 400 tons, will hold this superheated plasma in place. If successful, this could be the ultimate solution to clean, unlimited energy. But why is this fusion project so complex? And could it really revolutionize how we power the planet? Our world is at a tipping point. We've relied on fossil fuels like coal, oil, and gas for centuries to power our homes, industries, and vehicles. But now, with climate change worsening and resources running out, it's clear we need something better. The world is searching for a cleaner, safer, and limitless source of energy, and that's where nuclear fusion comes in. Nuclear fusion is what powers the sun. It's the process where hydrogen atoms are forced together, releasing huge amounts of energy. If we could recreate this process on Earth, it could give us nearly limitless energy, with none of the harmful byproducts like CO2 that are causing climate change. Plus, unlike nuclear fission, which splits atoms apart in today's nuclear power plants, fusion doesn't leave behind dangerous, long-lasting radioactive waste. And it uses hydrogen, the most abundant element in the universe, as fuel. Sounds perfect, right? The problem is, fusion is incredibly hard to achieve on Earth. To force hydrogen atoms together, you need temperatures of 150 million degrees Celsius, which is hotter than the center of the sun. You also need strong magnetic fields to contain this reaction and prevent it from getting out of control. This is a massive challenge, and scientists have been working on it for decades. The dream of nuclear fusion began in the 1950s, and by the 1980s, world leaders saw the potential for fusion to solve the planet's energy crisis. That's when they decided to team up and create ITER, the world's largest nuclear fusion experiment. The name ITER stands for International Thermonuclear Experimental Reactor, but it also means the way in Latin, symbolizing a path toward a new energy future. ITER is a global project with 35 countries, including Europe, the US, China, Japan, and more, joining forces to make it a reality. Construction of the ITER facility began in the south of France in the 2010s, and it's been a slow but steady process. The project's goal is to prove that nuclear fusion can work on a large scale and provide the energy we need to power our future. If successful, ITER could be the key to solving our energy problems, offering clean and endless power for generations to come. Once fully operational, ITER aims to achieve a groundbreaking milestone, producing 500 megawatts of output power from only 50 megawatts of input power, demonstrating an energy gain factor of 10. To do this, scientists and engineers need to construct a machine capable of reaching temperatures hotter than the sun's core, while controlling that heat with extreme precision. Let's explore the fascinating process of how it's all coming together. At the heart of ITER is something called a tokamak. This is a massive, donut-shaped chamber where the fusion reaction will happen. It's built to contain and control plasma, the superheated gas that fusion requires. Plasma is made when hydrogen atoms are heated to 150 million degrees Celsius. At this point, the atoms move so fast that they smash into each other, releasing enormous amounts of energy. But controlling something that hot? That's where things get tricky. To keep the plasma stable inside the tokamak, engineers rely on giant magnets. They're the most powerful superconducting magnets ever built. There are 18 D-shaped magnets, each weighing around 360 tons. That's heavier than a fully loaded Boeing 747. These magnets generate a magnetic field strong enough to contain the plasma, which prevents it from touching the walls of the tokamak. If the plasma escaped, it would cool down and the fusion reaction would stop, so keeping it contained is critical. But it's not just the magnets. The entire system is a carefully balanced mix of technology. Surrounding the plasma chamber is a vacuum vessel, a massive stainless steel structure that acts like a protective shell. This vacuum ensures that the plasma stays isolated from any outside air, which could interfere with the reaction. The vessel itself weighs 5,000 tons and is assembled from giant sections, each carefully welded into place. Every single weld has to be perfect because even the tiniest leak could be disastrous. One of the most impressive feats of engineering at ITER is the cooling system. The magnets and other critical components need to be kept extremely cold, just a few degrees above absolute zero, or negative 269 degrees Celsius. That's colder than outer space. This is achieved by a cryogenics plant that supplies liquid helium to cool the system. The cryogenics plant is the largest of its kind, producing about 25 tons of liquid helium every day to maintain these freezing temperatures. Without this extreme cooling, the superconducting magnets wouldn't be able to function properly. At the same time, inside the tokamak, the plasma is blazing hot, millions of degrees hotter than anything on Earth. So ITER is dealing with both extremes, the hottest and coldest temperatures known to science, all just a few meters apart. This delicate balance between extreme heat and cold is what makes the project so challenging. Getting all the parts of ITER into place is a logistical challenge too. The components of the tokamak, including those massive magnets, are being built by countries all around the world. Some of these parts are so large they have to be transported along specially designed routes. For example, sections of the cryostat, which encloses the tokamak, had to be shipped from India in pieces because the entire structure is too big to transport at once. The cryostat weighs nearly 4,000 tons and had to be carefully assembled on site, piece by piece, with no room for error. The assembly process takes place inside the tokamak building, which is a 7-story structure that rises 60 meters above ground and extends 13 meters below. This is where all the parts come together. Once everything is in place, powerful cranes are used to lower components into the tokamak pit, where they are fitted together. The building itself is designed to withstand earthquakes, with special seismic bearings placed under the foundation to absorb shock and protect the reactor during operation. Another critical element of the construction is the bioshield, a 3-meter thick wall of reinforced concrete that surrounds the tokamak. This structure is designed to protect the outside environment from any radiation that might be generated when the fusion reaction occurs. Inside the bioshield, workers have to be incredibly precise, ensuring that every component is installed correctly. The margin for error is practically zero. Any mistake could delay the project or cause significant damage to the reactor. Once all these systems are in place, it's time to turn on the tokamak. The first step is called first plasma, which will be a test run to make sure everything is working. This involves heating up the hydrogen fuel to create plasma, which will be contained by the magnetic fields inside the tokamak. If successful, this will be a major milestone in the project and will prove that the machine can generate the conditions necessary for fusion. However, achieving fusion is just the first part of the challenge. The real goal is to reach self-sustaining fusion. This means that once the reaction starts, it can keep going on its own without the need for additional energy. Scientists hope that once ITER is fully operational, it will produce 10 times the energy needed to start the reaction. For comparison, current nuclear fission reactors generate less energy than the amount needed to maintain the reaction. Fusion, on the other hand, has the potential to be far more efficient. But this isn't just about the energy produced, it's about safety and sustainability. Unlike traditional nuclear reactors, which rely on splitting heavy atoms like uranium, fusion uses hydrogen isotopes, tritium, and deuterium, which are much easier to obtain. They're also much safer. Fusion doesn't produce long-lived radioactive waste, and there's no risk of a meltdown like we've seen with fission reactors in the past. ITER is a monumental project, not only because of the scale and complexity of its engineering, but also because of the international collaboration behind it. Over 35 nations are involved in building this reactor, contributing resources, technology, and expertise. This level of global cooperation is unprecedented for a scientific project. In fact, 75% of the design, manufacturing, and assembly work has already been completed, and more is happening every day. While there have been setbacks along the way, such as technical challenges and delays, the progress being made at ITER is nothing short of remarkable. When it's complete, ITER won't be producing electricity for the grid, but it will serve as the blueprint for future fusion reactors. The lessons learned here will be critical for the next generation of fusion energy plants, which could start supplying clean, limitless energy to the world. If you enjoyed the video, don't forget to like, subscribe, and turn on notifications for more content. Leave a comment with your thoughts, and we'll see you in the next one.